I'm going to try to show you some polar areas being traced out so that you get a better sense of how exactly it works. As you can see, I'm starting with r equals 1, just a circle of radius 1, and going to kind of shade it in as theta increases from, let's say, 0 to pi over 2. And you can see that it's shading in the way you would kind of expect it. So it's like the unit circle, counterclockwise, not really an issue there. So let's try to move on to something a little more interesting. So I'll change this up to sine of t, or sine of theta. You can see that it switched to a circle of diameter 1 on the positive y-axis. And now let's watch what happens. So theta is increasing. And this is where I think people get a little confused about how it's tracing out the area. So you can see that theta is increasing, and as theta increases, r increases up to a certain point. So I'm about to get to pi over 2, which you can see it's decimal equivalent there. And there's half the circle. So what I would do is I'd actually just integrate from 0 to pi over 2 and then double it. But if I keep going, I get this. Let me reset this and just start at pi over 2. Get rid of that. And if I start tracing here, you can see it just starts there and kind of fills in. And let's move on to a different curve. So I'll reset my theta value, I'll clear my traces, and now I'm going to change it to a rose curve. So sine of, 3t. And you get the rose curve, and let's trace this out. So this one is, so you can see that it's filling in this first petal and doing a pretty good job of it. And then it finishes filling that in, and now we're filling in the second petal. And the third petal is coming up. There we go. And so that's actually how the area is filled in. As you've probably seen in class, what I like to do is just find one, and then I would triple it in this case. So I'm going to turn that off, clear my traces and reset, and take a look at a limison. So let's see. I have to make it tiny to fit on the screen. Okay, clear that. And here we go. So let's trace this out. So now this, if you look at it, it's between 0 and pi over 6. It fills in the part that was just filled in there. And then between pi over 6 and 5 pi over 6, it's going to fill in this inner loop. So that's, I'm approaching pi over 2, where r is negative. What is that? 0.25. And now from pi over 2 to 5 pi over 6, I finished the inner loop. And it's going to keep going, and here's where you end up getting in trouble. So it's about at pi, and if I just keep going, you can see it's going to start tracing back over this area, and that's what we want to avoid. So we have to be a little clever about it when we pick our bounds for integrating. And we'll talk a lot about that in class, or we probably already have talked about that. But I just wanted to show you how these things are traced out so that you get a better sense of why the bounds are important. And it's a little bit different from geometry and a little bit different from the regular area integrals that you're used to. So I hope this is helpful.